In this video, I will cover the concept of significant figures. Significant figures are what tells us how precisely we know a measured value, usually measured. And in some cases, we'll deal with exact values, which are not measured, but are direct counts of discrete objects or definitions of relationships between units. And we'll also deal with significant figures that come out of our calculator when we press equals to get the answer to a problem. Let me start by showing you the PowerPoint set that I present in class. With significant figures, we'll talk about measured data, which is where most of our work with significant figures is done. We'll also have counted and defined data, which are exact numbers, and calculated data. Now, when we deal with calculated data, we'll group those into two families. We have the multiplication and division, which follow one set of rules, and addition and subtraction, which follow another set of rules. We can define significant figures as all the certain digits plus one uncertain digit. And so to illustrate, let's say that we want to measure something, let's say perhaps a copper wire, and that red line there is my copper wire. And I've got two rulers with different degrees of precision. I have a ruler A, which for the sake of discussion, we'll say it measures in meters, although the units don't really matter for this discussion. It's actually the numbers themselves we're interested in, but let's just say it measures in meters. So ruler A is marked off at the integer level. You can see marks for 1 meter, 2 meters, 3 meters, 4 meters, and 5 meters is down at the end. Of course, the left-hand end is where 0 is, and the right-hand end is at 5 meters. And so let's say we want to measure that wire with ruler A. So we put one end of the wire at the 0 mark, we stretch the wire out, and I've dropped a little dotted blue line from the end of the wire down to the measurement scale, just to give you a better idea where the end of that wire coincides with the scale. And then up above, at the top there, I've got X decimal, X, 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 and dot, 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 dot. And those X's are where numbers would go. And I'm just using X's for fillers all the way down, but that does not mean that all those numbers are the same. So different X's can take on different numerical values, but each X represents a single digit. And what we want to do is see how precisely we can fill out that measured value in the positions where the X's are. Well, that first X, when I'm using ruler A, and for that matter, will still be when I'm using ruler B, that first X is a certain digit. So we talk about certain and uncertain digits. And you'll see we carry one uncertain digit because the first uncertain digit can be reasonably estimated. But after that, we really have no idea what the numbers are. So when I look at that red wire, look at where it ends, I can see that it is more than 1 meter, but less than 2 meters. So it is 1 point something. And so I know with certainty then that the first X is going to be a 1, right? The number in this position right here is a 1. Clearly, it's not a 0, because if that number could be 0, then the wire should end somewhere in this range between 0 and 1. And clearly, it's not a 2, because if that were a 2, then it would end somewhere in this range between 2 and 3. So clearly, it is 1 point something. And so that first X is a 1, and that is a certain digit. Okay, now I go and look at the second X, and I ask myself, what number would go in the position of that second X? Or in other words, the first X after the decimal point. Well, I don't have any further marks to guide me on ruler A. There are no smaller tick marks between the larger tick marks for the integers. So I'm forced to estimate how many tenths of the way is that between 1 and 2. Is it 2/10 of the way? Is it 3/10 of the way? And so if you ask several people what that is that 1.2? Is that 1.3? You might get different answers. Now, certainly there are, of course, bounds of reason. I would be rather puzzled if someone told me that that length was 1.9, because 1.9 should be almost up to the 2 mark. So there are some measurements that would not be reasonable, but if you were to record that as 1.2, it wouldn't be correct or appropriate to tell someone who recorded it as 1.3 that they were wrong, because 1.2 and 1.3 are both reasonable estimates of where that wire ends, right? We don't have any marks to guide us, so we are forced to estimate. And so there may be some differences of opinion within a slight range. But certainly, say I want to call it 1.2. 1.2 is a reasonable estimate. It might be 2/10 of the way between the 1 and the 2. It certainly looks like it's closer to the 1 than it is to the 2. So 1.2 would be good. And so we might express the length of this wire as 1.2 meters. And so this ruler then is letting us express that measurement to 2 significant figures, where the first figure is known with certainty and the second figure is an uncertain figure, or one that has been estimated. And once we reach the first uncertain digit, there's no point going any further. So if I know this one is a 1 and I think this one is a 2, then I have no idea what that third x is, because this first uncertain figure, that's in the tenths position. That says I could be off by about, give or take, 1/10 of a meter. Well, this next x represents the hundredths of a meter, and it takes 10 hundredths to make just 1/10. And so if I'm not really sure about the tenths, I can't possibly know the hundredths. Okay, and I can't even give a reasonable estimate of that figure. So I would have to cut it off at that first decimal place and say 1.2 meters might be how I would express the length. But notice that the number of significant figures you can report in a measurement depends on your measuring device. Some measuring devices are more precise than others just by their nature, by the way they're made. So look at ruler B. Ruler B has these small tick marks in between the larger integer marks. So now I have it marked off not merely at the integer level, at the whole meters like I did in ruler A, but I've got marks for tenths of a meter. And now if I take that same wire and again line up one end of the wire with 0 and stretch it out and see where the other end of the wire coincides with the measurement scale, I can now see that it is more than 1.2 meters, but less than 1.3 meters. Notice now that second digit is no longer an estimate. I now know that digit with certainty. I can see that it extends past 1.2, but doesn't make it to 1.3, meaning it is 1.2 something. So now I can fill in 2 x's with certainty when I use ruler B. I know that the first x is a 1, and I know for sure the second x is a 2. And now I can go on to estimate the third x. And so I might look at that and say, well, I think that wire ends right in the middle between the 2 marks. I think it's midway between 1.2 and 1.3. Now, if I draw that conclusion, then I'll say that's 1.25, right? 1/2 or 5/10 of the way between marks. So I might record that as 1.25. So ruler B is letting me express the length to 3 significant figures, where the first 2 digits are certain and the third digit is uncertain. And so you fill in your digits until you get the one that you don't know for certain. And you can carry that first uncertain digit because you can reasonably estimate what that value is. But again, beyond that first estimated digit, you have no idea. So it would not be appropriate to try to get a number for the next x. So we can report that as 1.25 meters, where the 1 and the 2 are known with certainty, and the 5 has been estimated. And again, there may be a difference of opinion on what that third digit is. Somebody might say, no, I don't think it's quite in the middle. I think it's maybe a little to the right of the middle. Maybe I want to record it as 1.26. And somebody else might say, no, I think it's actually not quite to the middle. I think maybe it's 1.24. So there might be some difference of opinion in what that estimated digit is. So you, again, report all the digits that you know for certain, plus 1 that has been estimated. And that's what significant digits or significant figures consist of. So all the certain digits plus 1 uncertain digit, one that you had to estimate. Now, this wire here in this example was somewhat more than 1.2 meters, right? And we had to estimate 1.2 what? What was that next digit? Well, let's say that I measure a wire that's just a hair shorter. And now when I put that wire against ruler B, it looks like the end of the wire exactly coincides with the 1.2 meter mark. And the question then is, in this case, would it be okay to write the length as 1.2 meters? Because after all, it ends right on that 1.2 mark, or so it seems. But there's a problem with that. If I write that length as 1.2 meters, then it doesn't look like it's any more precise than if I got the length from ruler A, because on ruler A, which is not as finely calibrated, I might report a length of 1.2 meters. So reporting this one as 1.2 would then make it look like ruler B is no more precise than ruler A. So what I should do in this case is write the length as 1.20 meters. And a lot of times people don't really regard those zeros at the end like they should. They think, oh, 0 adds nothing, so I'll just write it as 1.2. But in science, 1.2 and 1.20 do not have the same meaning when they refer to measurements. 1.2 means I know the value, give or take about 1/10 of a unit. Something that is reported as, say, 1.2 meters long could be between 1.1 and 1.3. And to the nearest 1/10, 1.2 is our best estimate. Now, 1.20 means that the value lies somewhere between 1.19 and 1.21. And to the nearest 100th of a meter, 1.20 is our best estimate. Calculators are bad about truncating trailing zeros. We're going to find later when we use calculators to do calculations on measurements, and when our answer comes not from a direct measurement, but from a calculation done on measurements, we'll find that usually the calculator gives us too many figures. And usually we have to round it back because normally it gives us more figures than we can reasonably be sure of. But the exception is when the number ends with trailing zeros that are significant. Calculators tend to truncate trailing zeros. So in that case, you may get fewer significant figures than what you should have. Okay, and we'll talk about that later. Okay, so if I say that wire is 1.20, that would be my way of saying I believe it ends right on that 1.2 meter mark. If I think it's just a slight bit to the left of it, I might report it as 1.19, right? Almost to that mark, but not quite. If I think it's a little over that mark, I might record it 1.21. So it's a little bit past it, whereas 1.20 is right on the mark as far as we can tell. Okay, so that 0 is important. You take that 0 off, it makes the measurement from ruler B look no better than ruler A. But notice that 0 at the end there does not change the numerical value of the length. What it changes is the precision. Okay, and so what makes a 0 significant is not its ability to change the numerical value. It's not that its presence or absence changes the numerical value. It's that its presence or absence changes the precision with which we know the measurement. Now, you've seen by these examples that the measuring device you use determines the number of significant figures. But yet, when you read a scientific paper, you shouldn't have to write to the scientist and ask permission to visit their lab so you can inspect their instruments to figure out how many significant figures their measurements have. If the person who's reporting the measurements is reporting them correctly, it should be possible to determine the number of significant figures just by looking at how they reported their numbers. So if I'm using ruler B and I report it correctly, I will say 1.20 and not merely 1.2. But if I was using ruler A, I would report 1.2. I would not report 1.20 because that would make it look like there was more precision than there really was. But if the person who is reporting the measurements is doing so correctly, it should be possible to just look at their numbers and tell how many figures are significant. And so to do that, we need some rules. And so I'm going to give you 5 rules. The first rule is very simple. It says all non-zero digits are significant. So all you have to do, if the number does not have any zeros, is just count the number of digits in the measurement. Okay, because if they're all non-zero and the person who reported it correctly, then every one of those non-zero digits is significant. So just count the digits, and that's the number of significant figures. So all the uncertainty comes in, or all the confusion comes in when there are zeros, because sometimes they're significant and sometimes they're not. So the following 4 of these 5 rules will deal with how to handle the zeros. So the first rule, very easy, all non-zero digits are significant. But what if your measured number contains some zeros? First rule I'll give you is that zeros at the beginning of a number are not significant. So if you start at the left-hand end of the number, proceeding from left to right, no zero can be significant until you have encountered your first non-zero digit. 1 or more consecutive zeros at the beginning of a number are not significant. They're just placeholders to locate the position of the decimal point. The significance begins with the first non-zero digit. Okay, next rule tells us that zeros to the right of a decimal point are significant if they are preceded anywhere in the number by significant digits. I will just wait a little bit to delve into that when we get to the examples, and I think the example will make it clear. But notice that zeros to the right of a decimal point, they may or may not be significant because there's an if in there. If they're to the right of a decimal point, they're significant if they're preceded anywhere in the number by significant digits. But what if they're not preceded anywhere in the number by significant digits? Then they're not significant. Okay, here's another one. Zeros between significant digits are significant. Kind of a sandwich effect, right? The significance of the digits around them rubs off on the zeros in the middle. So 1 or more consecutive zeros between significant digits are significant. And then here's probably the most troubling one of all. If a number ends in zeros and a decimal point is not shown, the number of significant figures is indeterminate. In other words, we can't tell. So sometimes they're significant, sometimes they're not. Sometimes some of them are significant and some are not. And by the way, this idea about the number of significant figures being indeterminate, that's the way that I look at it. A lot of other people look at it, but I should tell you, not everybody plays by that rule. There are some folks who say that since I can't tell whether they're significant or not, I'll just assume they're not. And so if a number has trailing zeros and no decimal point at the end, some people will just count the non-zero digits and say, that's how many significant figures it has. But personally, I think it's better just to say we can't tell in that format. And there is a way around that if you're the one that measured it. See, when it's written with zeros at the end and no decimal point, which of course implies that the decimal point is at the right-hand end of the number. But if it's not explicitly shown, then we really can't tell about the significance of those zeros. Really, only the person who measured the number knows for sure how many of those zeros are significant. Now, if you are the one who measured it and you know how many are significant, there is a way to rewrite that number to remove that ambiguity and make it clear how many significant figures it has. And I'll be showing you how to do that. Okay, so those are your rules, and we're going to apply those rules to some examples. So you might want to write these rules down, right? Pause the video if you need to, get those rules down, and then see if you can work out how many significant figures are on the next page as I show you some measurements. See if you can apply those rules and figure out how many figures are significant. Okay, so here we go. Some examples. Okay, and these are all physical measurements. Okay, first couple of them come right from the ruler example that I just gave you. 1.2 meters, 1.25 meters. Then let's look at a mass measurement where you put something on the balance pan and it reads 0.0027 grams. Okay, then a very precise length measurement, 6.000 meters. Then another mass measurement, 10.002 grams. Another mass measurement, 0.0050 grams. Okay, and then finally, 50.0500 grams. Now, you might want to pretend like this was a graded quiz. And if you've got those written down on a sheet of paper, next to each one, indicate the number of significant figures. And by the way, I did not give you any that are indeterminate in this example, anywhere you can't tell. So all of these, you should be able to come up with a definite integer, right? Like 1 or 2 or 3 or 4, some number of significant figures, which will be an integer, a whole number, because digits only come in whole numbers, right? You can't have 1.5 digits. So take a moment to put down how many significant figures you think are in each of those measurements. Okay, and pause if you need to get it written down. Okay, and here we go. So what are the answers? Well, remember that the first two are very easy because we have a rule that says all non-zero digits are significant. So when I look at the first measurement, I've got two non-zero digits, a 1 and a 2. I just count the digits. There are 2 digits there. Okay, so I've got 2 significant figures. The second one is equally easy. It's also got all non-zero digits. So I count the digits. I've got a digit here, digit number 1. There's digit number 2. There's digit number 3. There are 3 digits in that number. All non-zero digits are significant, and so it has 3 significant figures. Okay, now we get down to the measurements that have zeros in them. So how about 0.0027 grams? Well, remember, we have a rule that says zeros at the beginning of a number are not significant. And so this can be a single zero or it can be a chain of consecutive zeros. So here I've got 3 consecutive zeros before I get to my first non-zero digit. I've got 3 consecutive zeros. These zeros all count as zeros at the beginning of a number. And zeros at the beginning of a number are not significant. So none of those zeros are significant. That leaves me the 2 and the 7, okay, the non-zero digits, which are always significant. And therefore, I have 2 significant figures. Now, what may have confused some of you is you said, well, there's something about zeros to the right of a decimal point being significant. Well, remember, there was a qualifier, right, in that statement. It said zeros to the right of a decimal point are significant if they are preceded anywhere in the number by significant digits. But these zeros after the decimal point are preceded only by a 0, which as a 0 at the beginning of a number is not significant. So all 3 of these zeros then count as zeros at the beginning of a number. And even the zeros after the decimal point are not significant because the if statement is not satisfied. They're not preceded by anything significant. So they're all just zeros at the beginning of a number, leaving only the 2 and 7 to be significant, giving us 2 significant figures. Okay, now we come to 6.000 meters. Okay, now we have zeros after a decimal point like we did here, but whereas the zeros after the decimal point here were preceded only by another 0, here the zeros after the decimal point are preceded by a 6. And of course, we know that 6 is significant, right? All non-zero digits are significant. So that 6 is significant. And then we have the rule that says zeros to the right of a decimal point are significant if they are preceded anywhere in the number by significant digits. Okay, and they're preceded by that 6. So this time the if clause is satisfied. And so those 3 zeros are significant, as is the 6. So we have 1, 2, 3, 4. Okay, so we have 4 significant figures. Okay, next number, 10.002. Well, notice that we can take those 3 zeros, both the one before the decimal point and the 2 after the decimal point. Notice they are sandwiched in between 2 significant digits, right? Because there's a 1 in front of the first 0, which non-zero digits are always significant. There's a 2 after the last 0. And again, non-zero digits are always significant. So we have a chain of 3 zeros that are surrounded by significant digits. And we have a rule that says zeros between significant digits are significant. So those 3 zeros are significant. And of course, the 1 and the 2 are definitely significant. So everything there is significant. So 1, 2, 3, 4, 5. Okay, and we have 5 significant figures. Now, if you focused in on those zeros after the decimal point, okay, you could also conclude they're significant by another rule. Zeros after a decimal point are significant if they're preceded anywhere in the number by significant digits. And even if you weren't sure about that 0 immediately to the left of the decimal point, the 1 over there, being a non-zero digit, is definitely significant. So zeros to the right of a decimal point preceded somewhere in the number by a significant digit, okay, makes those 2 zeros significant, and then that 0 is sandwiched in between significant digits. So no matter how you look at it, all of those zeros are significant, and we have 5 significant figures. Okay, how about 0.0050 grams? Okay, how many figures are significant there? Well, the first 3 zeros are zeros at the beginning of a number. And we have a rule that says zeros at the beginning of a number are not significant. And even if we look at those second two zeros and say, well, look, they're after a decimal point. Well, yes, they're after or to the right of a decimal point, but they're not preceded by anything significant. There's a zero at the front there. So all of those three zeros just count as zeros at the beginning of a number. None of those are significant. But of course, that 5 being a non-zero digit is significant. And then that last zero is a zero which is both to the right of a decimal point and preceded by a significant digit, the 5. Although the other two zeros are also to the right of a decimal point, they are not preceded by anything significant. Again, they count as zeros at the beginning of a number. No zero can be significant until you have encountered your first non-zero digit. So the 5 is significant and the 0 following it is significant, making the number have two significant figures. And then finally, we've got here, all the digits are significant. Obviously, the two 5s are significant. They're non-zero. We got a couple of zeros sandwiched in between the two 5s. Zeros between significant digits are significant. And then the last two zeros are to the right of a decimal point and are preceded by a significant digit, that 5 there. So everything there is significant. So if you count the digits, 1, 2, 3, 4, 5, 6. There are 6 digits there. All of them are significant. Okay, let's look at some more examples where we will include some numbers that are of indeterminate number of significant figures. So some of these will have definite integer answers. There'll be a definitive number of significant figures, and some we won't be able to tell. Okay, and so let's have a look at these. Okay, the first one, 100 millimeters. The number of significant figures here is indeterminate because the number ends with zeros and no decimal point is shown. Okay, so our answer there is going to be that we have an indeterminate number of significant figures. See, normally, if a digit is not significant, we try to avoid writing it. But in the case of zeros at the end of a number, we might be forced to write them even if they're not significant, because if let's say that last zero was not significant, okay, if I deleted it, right, if I erased it, the number would look like 10, or look like 10 millimeters. But there's a big difference between 10 millimeters and 100 millimeters. So if I took that zero off, it would change the number. Okay, even if the zero was not significant, removing it would change the number. See, I don't show the decimal point explicitly, but when you don't see a decimal point, it's assumed to be at the right-hand end of a number. We have an implied decimal point. And so that zero may not be significant. It might just be there to locate the position of the decimal point. It could be that neither one of those zeros are significant. But again, if I delete both of those zeros, it looks like 1 millimeter. And that's even more different from 100 millimeters. So I can't tell whether the uncertainty lies at the hundreds position or the tens position or the 1. If neither of those zeros is significant, that means that the 1 you see there is already the uncertain digit, that is already an estimate, and therefore we can't have any idea what the other two positions, what numbers go in there. And of course, we're just filling in zeros as placeholders in that case to make the number the right size. In that case, the number is only known to within, give or take, about 100 millimeters, and the true value is somewhere between 0 millimeters and 200 millimeters, with 100 millimeters being our best estimate to the nearest 100. That would be the situation if neither of those zeros are significant, and the number had only one significant figure, meaning the 1 was already an estimated digit. It could be that the first zero is significant and the second one is not. In this case, the uncertainty first appears in the tens position. And we know it give or take about 10 millimeters. The true value is somewhere between 90 millimeters and 110 millimeters. Or in other words, 100 millimeters, give or take about 10. In this case, the 1 is known with certainty, but the first zero in the tens place has been estimated. And if we're not even sure how many tens of millimeters we have, we can't know how many individual millimeters we have. So in that case, we would have two significant figures, and we could nail it down to only give or take about 10 around the nominal value of 100. It could be that both of those zeros are significant, in which case that last zero is the one that's been estimated. Then in that case, the 1 is known with certainty, the first zero is known with certainty, and the second zero is an estimate, meaning that the actual value lies somewhere between 99 millimeters and 101 millimeters, or give or take about 1 millimeter around that nominal value of 100 millimeters. Okay, so again, the zeros affect the precision. Okay, what makes them significant is when they improve the precision, not their ability to change the value. Okay, now let's go to the next one. 10.0 centimeters. Well, now we're back to an ordinary measurement. And remember, zeros after a decimal point or to the right of a decimal point are significant if they're preceded anywhere in the number by significant digits. And 1, of course, as a non-zero digit is clearly significant. So that makes this 0 after the decimal point significant. It's to the right of a decimal point. It's definitely preceded somewhere in the number by a significant digit. But that puts the 0 in the middle, being between significant digits. Now that we've identified that ending 0 as significant and that 1 is significant, this 0 is now between two significant digits. So it too is significant. So we've got 3 digits there, all of which are significant. Okay, so we have 3 significant figures. Okay, now we got another one where we can't tell. We have 1,000 milliliters, and there's no decimal point shown. Oh, and by the way, if you do show a decimal point, that is a quick way of saying that you know all the zeros, that they're all significant. Or I guess the last one could be an estimate, but or would be an estimate. But putting a dot, explicitly putting a dot would say that all those zeros are significant. Okay, but in this case, we don't show a dot. Okay, so only the person who measured this knows for sure how many of those zeros are significant. Again, it could be that only the 1 is significant, in which case that's already your estimated value, and the true value lies somewhere between 0 milliliters and 2,000 milliliters. That would have only 1 significant figure. Okay, or maybe it has 2 significant figures, where the first 0 is an estimate, but can be reasonably estimated, and the last 2 we have no idea, they're just placeholders. Then we could be off by about 100 either way. So we're somewhere between 900 milliliters and 1,100 milliliters, with 1,000 being our best estimate to the nearest 100. Or it may be that the estimated 0 is this second one here. So the one that's in the tens position. So that now we know it's somewhere between 990 milliliters and 1,010 milliliters. Or in other words, give or take about 10 milliliters around that nominal 1,000 milliliter value. That would have 3 significant figures. If it has 4 significant figures, then that means that last 0 is the one that's been estimated. So we can nail it down between, give or take about 1 milliliter. So now our range of uncertainty is from 999 milliliters to 1,001 milliliters. So as I make more and more of those zeros significant, I don't change the number. It's 1,000 as I go all the way across there, saying none of them are significant, or this one is significant and the other 2 are not, or these two are significant and that last one is not, or all three are significant. As I make those changes, I'm not changing the value of the number, right? It's 1,000 in each case. What I'm changing is the uncertainty around that number. You might imagine drawing a number line and you mark off, you put a dot at 1,000, that's where your measurement falls. But then you could put left and right pointing arrows along the number line to show the uncertainty. You know, how far could you be off of that 1,000? And so you might be give or take about 1, might be give or take about 10, might be give or take about 100, or even give or take about 1,000, depending on the significance of those zeros. And so this is another one that we can't tell by looking at it. Only the person who measured it knows for sure what it has. Now, again, as I said, not everybody plays by that rule. Some people will say, well, if I can't tell whether they're significant or not, I will just assume they're not. Those people would take that number 1,000 without the decimal and say it has one significant figure. But on my quizzes, the answer I'm looking for is that it's indeterminate, that we really can't tell by looking how many of those zeros are significant. Your master in chemistry homework might use the word ambiguous. And so ambiguous is another word for indeterminate. They both mean you can't tell. Now, as I had mentioned a little while ago, if you actually explicitly write the decimal point, that is a shorthand way of indicating that all of the zeros are significant up to that decimal point, meaning our uncertainty then lies at the units level, okay? And we know now with that decimal point there that we've got this thing nailed down between 999 and 1,001, right? Or give or take about 1 milliliter. Okay, so the decimal point will tell us that all those zeros are significant and therefore that it has 4 significant figures. And then of course this one is easy, right? All I've done here is added a 0 after the decimal. So 1 is obviously significant. It's a non-zero digit. 0 at the end there is after a decimal point and preceded somewhere in the number by a significant digit, which makes that 0 significant. And then these 3 zeros are then in between significant digits, and so they become significant. And so everything you see there is significant. And so 1, 2, 3, 4, 5, right? And so that has 5 digits, all of which are significant. And so 5 significant figures. Okay, now I had told you that when I just wrote 1,000 milliliters, that written in that form, where a decimal point is not explicitly shown, we can't tell how many figures are significant. It could be only 1, it could be 2, it could be 3, could be all 4, right? So I can't tell by looking, is that known give or take about 1,000, give or take about 100, give or take about 10, or give or take about 1? In other words, where is the estimated 0? Where is the first time I encounter an uncertain digit? And only the person who measured that knows for sure, right? Because it's written in a way that we can't tell. But there is a way to avoid that ambiguity. And this will show you yet another benefit of scientific notation. So let's write this so it has 1 significant figure, so it has 2, so it has 3, and so it has 4. Now, you may have studied scientific notation before and thought of it as a good way to represent numbers that are either very large or very small. Because normally we don't like to write a number as an ordinary decimal number that's going to have a long trail of zeros at the end, or going to have a decimal point and a long trail of zeros before you get to the first non-zero digit. And so numbers that are either extremely large or extremely small, scientific notation can be helpful. But here's another way that scientific notation is useful. It can take ambiguous numbers like that 1,000 milliliters and make it clear how many significant figures it has. So if you are the person who measured that, and you know that it has only one significant figure, then you can write it 1 times 10 to the third. When you write a number in scientific notation, only the mantissa, or the part that comes before the x10, that's the only part that is significant, that conveys information on significant figures. So the power of 10 just gives you the size of the number. It indicates size, but not precision. All the information on precision is in the mantissa, or the number that comes before the x. So keep that in mind. Never look at the exponent when you're trying to gauge the number of significant figures. The exponent, the power to which 10 is raised, has no bearing on the number of significant figures. That information is solely in the mantissa. So when I look at that 1 there, okay, I've got a single digit mantissa. So now, even if I'm not the person who measured it, I know how many significant figures it has. It has 1 significant figure. Now, if the person who measured this knows that it actually has 2 significant figures, then they should write it like this: 1.0 times 10 to the third. Now that still has, still 1,000, right? 1.0 times 10 to the third is still mathematically equivalent to 1,000. If I remove the power of 10, I would have to move the decimal point 3 places to the right. I would have to insert extra zeros to jump over. But for both of those numbers, in the end, I would have 1,000. So they're both 1,000, but the second one there is more precise than the first. Now, as you might imagine, if we knew it had 3 significant figures, we would write it like this: 1.00 times 10 to the third. And if we knew that it had 4 significant figures, we could write it 1.000 times 10 to the third. Of course, in that last case, we could also write 1,000 and put the decimal point explicitly to show that all those zeros are significant. But of course, notice you should never do that with the first 3 cases, 1, 2, and 3. If you were to write any of those as 1,000 decimal, you would mislead the reader into thinking that it had 4 significant figures when it really has only 1, 2, or 3. So in those first 3 cases, we have no choice but to write it in scientific notation. A lot of times we'll have a choice. We could write it either as an ordinary decimal number and still make the number of significant figures clear, or we could write it as scientific notation. But in these the first 3 of these examples, we have no choice. The only way to make the number of significant figures clear is to write it in scientific notation. So that is yet another benefit of scientific notation. But not all numbers come from measurements, which have uncertainties. Of course, measurements, physical measurements, always have uncertainties. But sometimes we count discrete objects. That is, objects that only come in whole numbers. And numbers like that are considered to be exact. So let's say that somebody makes the statement, there were 15 cars in the parking lot. And somebody asks you, how many significant figures are there in that number? Now, the mistake you might make at first is to say, well, I see 2 non-zero digits there, a 1 and a 5. And I know that non-zero digits are always significant. I see 2 non-zero digits, so it has 2 significant figures. That's not the right answer, but that's a conclusion that you might first come to. Okay, now what's wrong with that? Saying that that has 2 significant figures certainly sounds reasonable, right? 2 non-zero digits. Non-zero digits are always significant. But remember that significant figures include all the digits that are known with certainty plus 1 that is estimated, right? That has uncertainty. So if that number was going to have 2 significant figures, that would mean that the 1 is known with certainty, but the 5 is an estimate. And we normally assume plus or minus 1 in the estimated digit. So you would be saying, I'm not really sure how many cars there are in the parking lot, but I tell you what, it's somewhere between 14 and 16. Now, that's not what you intend to say, right? I mean, if you measure a piece of string and you say it's 15 inches, well, it may not be exactly 15 inches, right? Because inches don't have to come in fractions. I mean, they don't have to come in whole numbers, excuse me. They don't have to come in whole numbers. They can come in fractions. The length of a string is continuously variable, okay? It's not confined to integers. So the 15 inches of string may not be exactly 15, okay, but it's probably somewhere between 14 and 16. So in that case, a two significant figure number would make sense. But if you count 15 cars in the parking lot, that's exactly 15, no more, no less. Right? You can't have a fraction of a car. So, you know, with the 15 inches of string, you could say, well, that this looks like 15, it's really 14.999. But you don't look at cars in the parking lot and say that just looks like 15, but maybe it's 14.999 cars. Well, you know, how do you have 0.999 of a car? So what that number really is, even though we don't normally write it that way, that number is really 15.000000 dot, 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 with the zeros going on forever because there are 15 whole cars plus no tenths of a car, no hundredths of a car, no thousandths of a car, and so on. And I could go on forever writing those zeros. Of course, numbers that are inherently integers, like counts of discrete objects, you never actually write those zeros. But in the back of your mind, you know that they're there, right? That if the number really is exactly 15, then that means there are no tenths or hundredths or thousandths and so on. And therefore, because those zeros go on forever, the number of significant figures is infinite because we know that zeros after a decimal point are significant if they're preceded anywhere in the number by significant digits, which they are. And then there's an infinite number of those zeros after the decimal point that we never usually write any of them, okay, for numbers that are inherently integers. But again, in the back of our mind, we know that they are there, okay? And so it got an infinite number of significant figures. So notice the context of the number is important. If the 15 refers to 15 cars, it's got infinite significant figures. If the 15 refers to 15 inches of string, that's only two significant figures. And sometimes people make a mistake if it ends in 0 because they try to say, like this statement, there were 20 students in the classroom. And they might say, oh yeah, that ends with a 0 and there's no decimal point shown. And I learned that when a number ends with zeros and there's no decimal point, that the number of significant figures is indeterminate. Well, that's true of measured data, okay? That's true of measured data where there's going to be some inherent uncertainty. But you don't measure students in a classroom, you count them, right? And so if I say there are 20 students in a classroom, no one's going to say, well, maybe it's 20.0001 students and it just looks like 20 students. We know that 20 students is exactly 20 students. Okay, people, like cars, don't come in fractions. So that number has to be exact, which means really we have 20 students and no tenths of a student or hundredths or thousands or 10,000s. And we can go on forever writing zeros like that, because in a number that is an exact integer, that means all the places beyond the decimal point are 0. We know that zeros after a decimal are significant if they're preceded anywhere in the number by significant digits. And there is an infinite trail of zeros, so we have an infinite number of significant figures. So it's true whether it ends with a non-zero digit or whether it ends with a 0 digit. If the number comes from a count of discrete objects, and by this I mean things that would never be cut into fractions, like cars in a parking lot, people in a room, pennies in a piggy bank, anything that you would only take in whole numbers. Counts of discrete objects are of infinite precision because they're known exactly. And you think about it, it makes sense that the number of significant figures is infinite, because if you had any finite number of significant figures, then you could make the number more precise by obtaining additional significant figures. But if a number is exact, its precision cannot be improved on. And so the only way that can come about is if we have an infinite number of significant figures, because then there's no way to increase the number of significant figures. If I gave you any finite number, if I gave you 1,000,000 significant figures, you could make it more precise by getting 1,000,001 significant figures. So an exact number would have to have infinite significant figures. So it cannot be made any more precise because it is exact, which means it is as precise as it can possibly be. Okay, that's one place then where we get exact numbers. It's when we count discrete objects. That is, objects that only come in whole numbers. Okay, well now look at another case where exact numbers arises, and that is in defined data. When you give a definition of how one unit of measurement relates to another. So let's say you make the statement, there are 12 inches in a foot. And someone asks you how many significant figures are in that number 12. At first glance, you might say, well, let's, in error, of course, well, let's see. All non-zero digits are significant. I see 2 non-zero digits. I see a 1 and a 2, so 2 significant figures. Well, here's the problem with that. If that number has 2 significant figures, remembering that significant figures are all the certain digits plus 1 uncertain digit, which of course occurs at the end of the number. Uncertain digit's always going to be at the right-hand end of the number, because the numbers refer to tinier and tinier chunks of the measurement. As you go to the right, they represent smaller and smaller increments, right? And so the uncertain digit, the one you're going to estimate, is going to be at the right-hand end. So if that number were to have only 2 significant figures, that would say that the 1 is known with certainty, but that the 2 has been estimated. If we assume plus or minus 1 in the last digit, then that would say that number is somewhere between 1 and 3, and 2 is our best estimate. So you would be saying, well, I'm not really sure how many inches are in a foot, but I tell you what, it's somewhere between 11 and 13. Now, that's not what you mean to say, is it? When you say there are 12 inches in a foot, you mean exactly 12, no more, no less. You have to realize that the way that 12 inches in a foot was established was not by taking a 1-foot ruler and measuring it with a tape measure to see how many inches were present on that 1-foot ruler. That's not how it was done. A foot is defined as 12 inches, right? It was not measured to be 12 inches. It was defined to be 12 inches. So I could never measure something and know that I have exactly 12 inches, but I could define it, right? I could say, let a foot be exactly 12 inches. So what you're really saying then is that because you're saying a foot is exactly 12 inches, that there are 12 inches and no tenths of an inch or hundredths of an inch or thousandths of an inch and so on. And of course, that trail of zeros goes on forever, right? It's infinite in length. And these are zeros after a decimal point that are preceded in the number by significant digits, which makes them significant. And we've got an infinite number of them. And so the number has an infinite number of significant digits or significant figures. And this is true even if the number ends with zeros without a decimal point. That does not make it indeterminate. That only happens with measurements that have inherent uncertainties. It doesn't happen with counts of discrete objects or definitions of relationships between units, because those numbers are exact. So here's one that ends with zeros. There are 100 centimeters in a meter. Now, this arises from the definition of centi. Centi means 1/100th or 10 to the minus 2 of something. Okay, so 1/100 or 0.01 or 10 to the minus 2. But those numbers in that definition are exact. And so because a centi of something, including a centimeter then, basically a centi of anything, is exactly 1/100th of that thing, therefore it will take exactly 100 of those little pieces to make the whole thing. And so that number 100 is exact in this context because it comes from a definition. So the number is really 100.00000 going on forever. And again, all those zeros that are after the decimal point, okay, they are after a decimal point and preceded by something significant, which makes all of them significant. And you've got an infinite number of them. Of course, the two zeros between the 1 and the decimal are also significant because they're between the 1 and the infinite trail of significant zeros. So they're significant too, but I mean, you wouldn't even need to consider that, right? Because you've already got a trail of zeros after a decimal point that are significant and go on forever. So clearly, the number of significant figures is infinite. Okay, and now I've got some more examples coming up. Remember, I started you out with examples where the answer was always an integer. There was a definite number of significant figures. And then I went to a second run of examples where sometimes the answer was indeterminate. Okay, we could not tell. Well, now I'm going to do a set of examples where sometimes the number will be exact, okay, where that means the number of significant figures will be infinite. So now we have the big mix. Now we have everything. We're going to have whole number answers. We're going to have infinite. We're going to have indeterminate. Okay, we're going to have a little bit of everything. Okay, so here's some more examples. So we'll talk about numbers used in various contexts. 22.7 grams, 100 people, 100 milliliters, 100 centimeters in a meter, 10.0 seconds, 10 decimal millimeters, 15 pennies, and 3 feet in a yard. Now, why don't you take a couple of minutes to write down your answers, what you think these are, before I reveal them. You can pause the video if I'm going too fast for you, and get your answers down. Then you can self-grade and see how well you're doing with this. Okay, so let's say that you're ready now, or else you've paused the video and now you've unpaused it and you're ready to see how you did. And I hope you did very well. Okay, well, the first one starts out easy again. We've got nothing but non-zero digits, and all non-zero digits are significant in a measurement. The unit here is grams, so it is a measurement, right? It's a measurement of mass. So that ought to have 3 significant figures. Okay, how about 100 people? Now notice the number ends with 0, and there's no decimal point shown, but that does not make it indeterminate, because this is not a measurement. This is a count. This might be 100 people that went through a turnstile at a park or a zoo or something. So if it shows 100 people went through, that's exactly what went through, right? You don't have 100.5 people. Okay, so that should be like 100.00000 going on forever. So we're going to have an infinite number of significant figures. Now notice the next one, I get the very same number, 100, with no decimal point. But this time the context in which it arises is different. Now, instead of a number of people, we're talking about a number of milliliters. But you don't count milliliters, you measure them. The measurement of milliliters can be a fraction. Milliliters are continuously variable. Okay, unlike the people where you can have 99 people or 100 or 101, but you can't have anything in between. But you can have like 99.9 milliliters, right? You can have 99.999 or 100.01. So that measurement is continuously variable. And so by writing that without a decimal point, we don't know how significant that is. It could be that only the 1 is significant, that we only know it to within about 100 milliliters, that it's somewhere between 0 and 200, and 100 is our best estimate. In that case, neither of the zeros is significant, Only the 1 is significant, and we have one significant figure. Or it could be that we have it narrowed down to give or take about 10 milliliters, in which case the 1 is known with certainty, the second 0 is a reasonable estimate, and the second number, the first 0, that is a reasonable, is a reasonable estimate, and the third number, or the second 0, I have no, the one in the units position, I have no idea what that is. That could be anything from 0 to 9. In that case, I have two significant figures, and I'm somewhere, give or take, about 10. I could be between 90 milliliters and 110. And I would have only two significant figures there. The first 0 is already uncertain. That's my last significant figure. Or it could be that both of those zeros are significant. If that were the case, of course, I could put a 0. Put a decimal. If both zeros were significant, I could put a decimal to say they're both significant. But it could also be that I simply forgot to do that. Maybe they're both significant, but I forgot to put the decimal. So we really can't tell looking at it in that form. If it does have three significant figures, then it's known to give or take about 1 milliliter. And the actual value falls somewhere between 99 milliliters and 101. Okay, or 100 milliliters, give or take about 1 milliliter. But only the person who measured it, who actually obtained that number, knows for sure how precise it is. Those of us merely reading the number are left wondering. And so we have an indeterminate number of significant figures. We know it's either 1, 2, or 3, but we can't tell which. It certainly doesn't have 4 figures, right? Because it's not 4 digits there. So it certainly can't have 4 figures. So it's either 1, 2, or 3. Now, again, remember that idea of zeros being indeterminate. I told you that not everybody plays by that rule, right? So there would be some people that look at it, say it has only 1 figure, just to get you ready for that. Now, in my quizzes, number like that is regarded as having an indeterminate number of significant figures. That's the answer on my quizzes. But there are some people that would just say it has 1. But I don't like doing that, because what if the number came out of a calculator? Okay, it may not have just 1, it may have 2. So you have to know the context in which the number arose to know how many figures are significant. Okay, how about the next one? Again, we have 100 without a decimal. So notice, right, 3 numbers in a row there, 3 times in a row, we have 100 with no decimal point. But yet the answers are different every time. This time, well, actually not every time, the 100 people and the 100 centimeters in a meter will be the same answer. Different contexts is one is, of the two that are infinite, one is a count of discrete objects and one is a definition of the relationship between units. But there's exactly 100 centimeters in a meter because of the definition of centi. And so that one's infinite, just like the 100 people. So what I should say, there's only 2 different answers there, right? Infinite and indeterminate, but there's 3 contexts there, right? There's a count of discrete objects, okay, the people, a measurement, okay, the milliliters, and a definition, the centimeters in a meter. Okay, how about 10.0 seconds? Well, that 0 after a decimal point is preceded somewhere in the number by a significant digit. That 1 is definitely significant. It's non-zero. So we got a 0 to the right of a decimal point preceded by a significant digit. That makes that 0 significant. And then that middle 0, right, that is now between 2 significant digits. Okay, the 1 and the 0 that we've marked as significant because of that 1. And so therefore, all 3 digits there are significant. Okay, we have 3 significant figures. Okay, 10 decimal millimeters. Well, if that decimal wasn't there, we wouldn't be sure. It could either be 1 or 2 significant figures. But the decimal is a shorthand way of saying that that 0 is significant. And therefore, both those digits are significant, the 1 and the 0, and we have 2 significant figures. Okay, 15 pennies. Well, again, some people want to say, oh, indeterminate because there's no decimal. But that's only true when it ends with a 0 and it comes from a measurement. You got to have both of those conditions satisfied for it to be indeterminate. It's got to end with a 0 and it's got to be a measurement, right? Not a definition or a count of discrete objects. This is a count of discrete objects. So when we see 15 pennies in a jar, that's exactly 15 pennies, no more, no less. You could say it's 15.00000000 with the zeros going on forever. So infinite significant figures. And likewise, 3 feet in a yard, this is not a count, but a definition. We didn't measure a yard to be 3 feet. We defined a yard to be 3 feet. Okay, and so that's going to be infinite significant figures. Okay, so that's my rundown of measurements and counts of discrete objects and definitions of relationships between units. But there's one more situation to be considered, which actually will break down to 2 sub-conditions, and that is, we've not talked about what happens when the number comes out of your calculator display. So you didn't measure it or count it or define it, but rather you punched numbers into your calculator and you got an answer. And how do you account for the number of significant figures in an answer in your calculator? Okay, well, we're going to break those down into 2 families. Multiplication and division will follow one set of rules, or just say one, they're short rules, just one rule. And addition and subtraction will follow another rule. And I'm going to prove it for multiplication. You can take my word for it on division, but I'm going to illustrate the rule with multiplication. Okay, so let's say that I've got a rectangular piece of land, and I'd like to put a fence around my land. Let's say my land measures 11.21 meters in length and 4.22 meters in width. Okay, and so I want to know, if I build a fence around that, how much area is enclosed inside the fence? Well, you may know that area is calculated by multiplying length by width. So you could take those 2 numbers, 11.21 and 4.22, and multiply them together in a scientific calculator and see what you come up with. And when you do that, what you get in your calculator is shown in the middle in black. So there you see I'm multiplying 11.21 by 4.22. And if I punch this into a scientific calculator, I get 47.3062. Now, the question is, where should I round that off? How many figures are significant in that number? Well, if you were to interpret that number like you do data, right? If you were to treat that like with the rules you've been using for measured data, you would get a very wrong answer. Because when you take numbers that come from direct measurements, of course, this is not a direct measurement, it's a calculation result. But let's say that you treated it like a direct measurement. Well, our rules tell us that all non-zero digits are significant, and that zeros between significant digits are significant. And so that would mean that all the digits you see here are significant. Okay, the 4, the 7, the 3, the 0, the 6, and the 2 are all significant if you treated that like measured data. And that would mean that you have 6 significant figures. Count the digits, 1, 2, 3, 4, 5, 6. You would have 6 significant figures. But if that number really had 6 significant figures, then that would mean that all those digits were known with certainty except the 2 down at the end. And if we assumed plus or minus 1 uncertainty in that last digit, then we would say that the true area is somewhere between 47.3061 square meters and 47.3063 square meters. In other words, that you would know the area inside that fence to give or take about a 10,000th of a square meter. But what this page shows you is that the uncertainty in area is much larger than that. You see, this number, this area, is not measured it's calculated, right? You didn't get that area by going onto the land with some kind of instrument called an areanometer, right? And say, well, let me pull out my areanometer and measure the area. But rather, it's calculated. You may have used a meter stick to measure the lengths, but you didn't measure the area, you calculated it. So the uncertainty in area does not come from a direct measurement of area. It comes from errors in the measurements that led to that area. So you might be off in your measurement of the length, and you might be off in your measurement of the width. And if those numbers are off, then if you're using the wrong numbers in your calculation, numbers that aren't quite right, then your calculated area won't be quite right. So your area gets its uncertainty not from a direct measurement, but from errors in the numbers you started with in the calculation. So what I'm doing here in these other two calculations, you see one at the top in red and one at the bottom in blue. And these represent the upper and lower limits of area. What I did is assumed plus or minus 1 uncertainty in the last digit. And so I said that value that was nominally recorded as 11.21 meters could be as small as 11.20 meters or as big as 11.22 meters. And likewise, the width, which has a nominal value of 4.22 meters, could be as small as 4.21 meters and as large as 4.23 meters. So if you wanted to get the maximum possible value for the area, you would want both measurements to simultaneously take their upper limit. So we're letting the length go to 11.22 meters. We're letting the width go to 4.23 meters. So if the actual values here were really 11.22 and 4.23, and we multiply them together, then we get 47.4606 as an upper limit on the area inside that enclosure. But what if they take the lower limit simultaneously? So the length becomes 11.20 and the width becomes 4.21. Now we multiply them out and we get 47.152 square meters. Now, if you compare these three numbers, okay, the nominal value, compare that with the upper limit in red and the lower limit in blue, and you see that they differ by much more than merely a 10,000th of a square meter. They differ much more widely than that. So, you know, the upper limit is far more than 47.3063. Okay, the lower limit is far less than 47.3061. Right, so the actual range of possible areas is wider than what we would conclude if we treated the nominal value as having 6 significant figures. So how do we decide how many figures we should report? Well, there will be a nice little, short sentence rule that tells us how to round it, but I would rather you see that fall into place naturally. So for this first time around, we're going to just go back to the basic definition of what significant figures are. Significant figures, recall, are all the certain digits plus one uncertain digit. So we have to look at these digits and the number 47.3062 and figure out which of these are known with certainty and which of these have uncertainty. Remember, we can carry the first uncertain digit because it can be reasonably estimated. We cannot carry any uncertain digits after that. When I compare these three numbers, I find they all begin with a number 4. So the number 4, the number in that first position, the 4, is a certain digit because they all three calculations agree that a 4 belongs in the first position, whether you're taking the lower limit, the nominal value, or the upper limit. They all place a 4 in that position. Then we go on to the second one. the 7. Is that certain or uncertain? Well, let's see. The nominal value has a 7 as the second digit. The upper limit has a 7 as the second digit. The lower limit has a 7 as the second digit. So they all agree on the second digit. So that's also a certain digit. Then we move out to the third digit, which is a 3 in the nominal value. But this is where the numbers start to disagree. The nominal value puts a 3 in that position. The upper limit puts a 4 in that position, and the lower limit puts a 1 in that position. So it's in the third digit, the first place where disagreement occurs. And so that digit must be uncertain. And of course, once you encounter an uncertain digit, that's the last one you can report, because that one is a reasonable estimate. But beyond that, we have no idea. The only thing I would use the other digits for is if the next digit over is 5 or higher, I would round up. And if it's less than 5, I would leave it alone. That's all I use it for. So I'm allowed to carry 3 digits because the first 2 agree in all calculations, and the third one is where they start to disagree. Now, when I look at the nominal value, the fourth digit is a 0, so that's not enough to round up, right? That would have to be a 5 or higher. So I'm merely going to truncate the 0.62 and write the answer as 47.3 square meters. Now, again, if that next digit had been a 5 or higher, as I truncated the rest of the digits, I would have rolled that 3 up to a 4 and made it 47.4. But in this case, it's not 5 or higher. So I merely drop the 0.62, and my final answer is 47.3 square meters. Now, if we had to do it this way every time, it'd be an awful lot of work, right? But the good news is that you don't have to do this. You don't have to do a calculation 3 times just to decide how to round the answer in the nominal calculation. There is a short and simple rule you can use that will tell you how to round the number. But I wanted you to see it fall into place on its own before I revealed the rule. So you saw that just going back to the definition of significant figures and doing a very careful analysis, we concluded that it should have 3 significant figures. Well, the rule is going to tell us the very same thing. The rule for multiplication and division says the answer can only have as many significant figures as the number with the fewest significant figures. And of course, the numbers I start with come from direct measurements, and so I can follow the rules for data. And they're simple because they don't have any zeros, so you just count the digits. So 11.21 meters has 4 significant figures, and 4.22 meters has 3 significant figures. And so when you multiply numbers together, whether it's 2 numbers or 3 numbers or 4 numbers or 5 numbers, doesn't matter. You just go down the chain of numbers you're multiplying, and you count the number of significant figures in each, and the answer is limited to the number of significant figures in the number with the fewest. So in this case, 11.21 meters has 4 significant figures, but 4.22 meters has only 3 significant figures, and therefore our answer can only have 3 significant figures. And so we could have figured out immediately that the answer was going to be 47.3 square meters without having to do that calculation 3 times. And the rule is logical when you think about it, because what it's saying is like a chain is only as strong as its weakest link. If you've got a chain with links that can hold 200 pounds, but somewhere in the middle of that chain, one link can only hold 10 pounds. The maximum weight you can hang on that chain is 10 pounds. If you try to hang a 20-pound weight on that chain, even though all the links except one can hold 200 pounds and could easily hold that 20-pound object, but if there's a link in the middle that can only support 10 pounds, putting the 20-pound object on there is going to break the 10-pound link, and the chain will not support that object. So just as a chain is only as strong as its weakest link, A calculation is only, the answer to a calculation is only as precise as the least precise number that led to that answer. That's what it's saying. You can't have more information in your answer than in the data you started with. Okay, so the more significant figures you have, the more precise it is. And so you got one number has 4 figures of precision, one number has 3 figures of precision. So you're not going to do any better than 3 figures of precision in your answer. You're limited by that number with the least precision. And by the way, the same rule works for division. So this rule is both for multiplication and division. I've only illustrated it for multiplication, but the same principle holds for division. And now let's go on and look at addition and subtraction. And here we follow a slightly different rule. Now let's say that I have 2 pieces of string. One of them is a lot longer than the other. The shorter piece of string I can measure with a ruler that lets me nail down the length to the nearest thousandth of a meter or millimeter. And so carefully using that measuring device, I conclude that that shorter piece of string is 1.147 meters. Then I have a longer piece of string, and it's not so convenient to measure with that meter stick because I have to flip it end over end over and over. So let's say that I have some other device that is more suitable for measuring long lengths, but it doesn't let me narrow down the length as much. And with this device, I can only get it to 1/10 of a meter. And so I measure that longer piece of string with this other device that lets me resolve the length to within 1/10 of a meter. And I conclude that the length is 15.2 meters. Now, the question I'm going to ask is, if I were to lay these 2 pieces of string end to end, what would be the total or combined length of the 2 pieces of string? And of course, I would get that by adding the 2 lengths together. So here, I've added the numbers together in the classical way, as I'm sure you've all learned in grade school, right? Lining the numbers up by their decimal points and then adding them digit by digit. Okay, you've all done that since for many years now. But I'm doing something here that I bet you never did in grade school. I'm color coding the numbers to indicate their degree of certainty or uncertainty. A number shown in black is known with complete certainty. A number that is shown in red is uncertain, but can be reasonably estimated. And the true value probably lies somewhere plus or minus 1 around the reported value. And then numbers in purple, I have no idea what they are. Okay, they could be anything. Now remember when you were learning to add numbers in grade school and one number had more decimal places than another number? And your teacher said, well, just fill in zeros where you don't have any digits. Just fill in zeros to make them all the same length. Well, those are just zeros of convenience. Okay, they're placeholders. We don't really know they're 0. The measuring device did not tell us what digits were there. It did not allow us to estimate or resolve that length to any closer than 1/10 of a meter, right? It gave us a reading 15.2 meters, right? Those zeros there are just so we'll have something to add, right? So you don't have to say 7 plus blank is what, right? So your teacher said just fill in a 0 because there's nothing there. And of course, mathematically, adding zeros to something doesn't change its value. So it does leave it at 15.2. But if we knew those were zeros, it would mean the number was known more precisely. But notice you can't generate precision that's not there in the first place. Okay, if the instrument did not allow you to record to any better than 1/10 of a meter, you can't make it more precise just because you wrote zeros in there. That doesn't make them 0. So they're just placeholders. But of course, when you add the digits, you treat them like they're 0, even though they might not be, right? So you say 7 plus 0 is 7, and 4 plus 0 is 4. So you're treating them like 0. And notice I've also color-coded my answer. So remember, black is complete certainty, okay, complete knowledge. Red is partial knowledge. You're not sure, but it can be reasonably estimated. And you're probably within, give or take, one unit of that. And purple is, I have no idea. Now, how do I know how to color code the numbers in the answer? Well, remember what I said earlier with the multiplication problem. Your answer cannot have more information in it than the numbers you use to create it. Okay, you cannot create knowledge out of information that's not there. So when you bring down your digits, each digit must adopt the color of the least informative number. So a number that I think is 7 plus a number I have no idea what it is gives an answer I have no idea what it is. Okay, I might write it as a 7, but I really don't know what it is because I don't know what this one is. I don't know what that 0 is. Then a number I know is 4 plus a number I have no idea what it is gives an answer I have no idea what it is. I can't know what this is because I don't know what this is. But I mean, I might treat it as 0 when I add them together, but since I really don't know what this is, I can't know what this is. Then a number I know is 1 plus a number I think is 2 gives an answer I think is 3. Then a number I know is 1 plus a number I know is 5 gives an answer I know is 6. So notice only if all the numbers being added are black can the number and the answer be black. If I've got black and red, I'm going to get red. And then if I've either got black and purple or red and purple, either way, I'm going to get purple because I'm going to get the least knowledgeable color. Okay, you cannot have more information in the answer than in the numbers that was used to create it. It's another way of saying a chain is only as strong as its weakest link. Now notice I also filled in a leading 0 because that top number had only one number before the decimal point. So to make them the same length, I filled in a 0. And notice I used a different color. I used gray. Now here's why I did that. You know, we normally say that the significant digits in a number are all the digits you know for certain plus one that has been estimated. So you look at the 1 and the 1 and the 4, they're all known with certain, and the 7 is certainty, and the 7 is estimated. But what about that leading 0? Well, it's not a significant digit, right? Because we learned that zeros at the beginning of a number are not significant. But yet, that number is known with certainty. Because if that number was not known with certainty, then conceivably it could be a 1. Think about that, right? If that number was not known with certainty, then conceivably it could be a 1, right? We could be off by 1. But if it was 1, then it would be 11.147. You know, that would be very different from 11.147 be very different from 1.147. I mean, if someone, you're sitting on a bench, someone comes by and says, how long have you been sitting on that bench? Do you ever say to them, well, I don't know, I've either been sitting here 1 minute or 11 minutes, but I'm not sure. Somehow I always get those two times mixed up. Not sure whether it's 1 minute or 11 minutes. Would really be a weird thing to say, right? Because 11 minutes is more than 10 times longer than 1 minute. So you would never mix up 11 of something with 1 of something. And so that number, that 0 there, it's not a significant digit, but yet it's known with certainty. So I didn't want to make it a full-scale black because it's not significant, but yet it is known with certainty. So I decided, well, make it a gray because that's a lighter black. So that's the one exception, about numbers, significant figures being all the certain digits plus one uncertain digit. The only caveat to that is leading zeros are not significant, but yet they're known with certainty. So that's one exception to that rule. But of course, a number I know is 0 plus a number I know is 1 gives an answer I know is 1. So now I got my answer with its color coding, and I've got to decide how should I express it? Where should I round it? Well, remember, we're allowed to carry one uncertain digit, but no more. So we can carry all the black digits because they're known with certainty, and we can carry one digit that is in color. And of course, that'll be a red digit because it can be reasonably estimated, and we have to throw away the purple digits, which have no information at all. The only thing I would use it for is to round the 3, okay? If that had been a 5 or higher, I would have bumped the 3 up to a 4 as I truncated these, but it's less than 5, so I'll just throw away the 4 and 7, and I'll write my final answer as 16.3. So the properly rounded answer to that calculation is 16.3. And I worked it out here by a careful analysis of which numbers were known to which degree of certainty. And you might look at that and say, well, that makes sense. I understand what you did, but you mean to tell me that I have to get out my crayons every time I want to do addition so I can figure out how to round the answer? And the good news is, no, you don't. I just did this so you could see what's behind it. There's going to be a short and simple rule that will tell us how to round the answer without having to color code all the numbers and carry out this rather tedious analysis. And the rule I'm going to give you works not only for addition, which I've considered here, but it also works for subtraction. And the rule says the answer can only have as many decimal places as the number with the fewest decimal places. And so with that rule, I could have got this answer, I could have obtained this properly rounded answer immediately without having to color code anything. Now here, remember, you're not counting significant figures, you're counting decimal places. That is the number of digits that come after the decimal point. So the number 1.147 has 3 decimal places. There are 3 digits after the decimal point. The number 15.2 has only 1 decimal place. It's got 1 digit past the decimal point. And so again, I'm going to adopt the fewest decimal places because remember, the answer cannot be any more knowledgeable than the least knowledgeable number that led to it, right? You can't get more precision out of an answer than the least precise number that went into it. So 1.147 meters is known to within 1,000th of a meter, but 15.2 meters is only known to within 1/10 of a meter. 1/10 is larger than 1,000th. So we can't expect to resolve the answer to any better than 1/10 of a meter because our least precise measurement was only given to 1/10 of a meter. So we have 3 decimal places and 1 decimal place, and therefore our answer can only be known to 1 decimal place. Okay, so we've got a rule for multiplication and division and a rule for addition and subtraction. But what happens when you do mixed arithmetic and you have all these calculations going on at the same time? Well, what you have to do then is solve the problem part by part and keep track of the significant figure rules that apply in each part of the calculation. So sometimes you're doing multiplications and divisions, and you're using that rule where you count significant figures. Other times you're doing an addition and subtraction, and you're using that rule where you count decimal places. And it's better not to round off what's called the intermediate answers. That's the answer to one calculation that's going to be input to another calculation. It's best not to round the intermediate answers, but rather just put a little underline under the last significant figure. And then only when you get down to the end, then properly round the answer. Because every time you round the number, you change it a little bit. So in a long chain of calculations, if you round off every intermediate answer and then you use the rounded value in the next calculation, over the course of a long set of calculations, those little errors, those little rounding errors that are introduced might add up and throw off the final answer compared to what it would be if you did not round the intermediate answers. Now, sometimes it doesn't make a difference. You know, sometimes you could round every intermediate answer and then use the rounded value in the next calculation and still get the same final answer when you round it off to the proper number of figures. It can happen. Sometimes it doesn't make any difference whether you round the intermediate answers or not. But sometimes it does. And when it does make a difference, the better answer is always the answer you get without rounding the intermediate answers. So when I look at this calculation, of course, I'm going to go after the quantities in parentheses first, right? Parentheses takes precedence over everything. Now I don't think I can get my calculator on here, but let me see if I can get a pointer. And we'll get a pen. Okay, and so let's say that I first leave the 1.12 and then I'm going to calculate what do I have in parentheses there? Okay, where I have to add 3.8 plus 2.17. And that gives me 5.97. So in the parentheses, I'm going to write 5.97. Now you see, if that were my final answer, because I'm adding 3.8 and 2.17, I'm adding a 1 decimal place number and a 2 decimal place number. By the rules of significant figures, I could only express that answer to 1 decimal place, right? 2.17 has 2 decimal places, 3.8 has 1 decimal place. So by rights, I only have 1 decimal place. If that were my final answer, I'd write 6.0. But it's not my final answer. It's an intermediate answer. Okay, it's an answer to one calculation. It's going to be used as input in another one. So I'm going to put a little underline under the 9, just to remind me that that's the last significant figure. That if that were my final answer, it'd be 6.0. But when I do the rest of the calculation, I'm not going to multiply 1.12 by 6.0. I'm going to multiply it by 5.97. Okay, now let me draw my fraction bar. And then I'm going to leave my 1.4 right now. And then what it's being multiplied by, I'm going to try to crunch that down to one number. So I'm going to take the calculator and put in 17.4. Okay, hold on a minute. My calculator has gotten into some strange mode. Let me try to start again. Okay, there we go. Okay, so 17.4 minus 11.9. 6.315. And that's 6.085. Okay, now I'm going to carry out the multiplication on the top. And the underline is going to help me. Like this other one, I should have also on the bottom underlined the 0, right? Because I took 17.4, which has 1 decimal place, minus 11.315, which has 3 decimal places. 1 is less than 3. So I'm only going to have 1 decimal place there. So my point is there after the 6. Okay, so I don't multiply 1.12 by 6.0. I multiply 1.12 by 5.97, okay, to crunch that down to one number. So if that underline wasn't there, I might forget and think that both the 1.12 and the 5.97 have 3 significant figures. And see, now I'm back to multiplication, so I'm counting significant figures, not decimal places. And if I didn't put that underline, I might think I'm multiplying 2 3 sig fig numbers. But I'm multiplying a 3 sig fig number by a 2 sig fig number. So my answer is only going to have 2 significant figures. Now when I multiply this out, 1.12 times 5.97, I get 6.6864. Okay, 6.6864. Okay, so let me fill that in. 6.6864. Whoops. Let me just take my pen off. Okay, 6.6. I don't know why I put a stray mark there above the 8, but that's 6.6864. And notice I multiplied the whole thing, 1.12 times 5.97. But I've only got 2 figures, so I count 1, 2, right? And the second 6 is the last significant figure. So I might put a little underline under that. Okay, so 6.6864 with the second 6 underlined. So it only has 2 significant figures because 1.12 has 3 and 5.97 only has 2, even though you see 3 figures there. Okay, then on the bottom, when I multiply the 1.4 by the 6.085, okay, that's what I multiply. I don't multiply by 6.1. If that were that number in parentheses, if it were a final answer, it'd be 6.1. But I'm not going to multiply 1.4 by 6.1. I'm going to multiply 1.4 by 6.085. And when I do that, I get 8.519. And let me see, it just said you want to keep your ink annotations, and you had keep and discard, and there was no like cancel and stay in the PowerPoint. So let me see if I can get back to it. I should still have my ink annotations. trouble with writing with this tablet is that if your hand just brushes the tablet, you get some command you weren't expecting. Okay, so I was trying to say that I'm going to multiply the 1.4 by the 6.085, and the answer is going to be 8.519. Okay, but let's see what happened there. Okay. I've lost my pen. May have to do this with a mouse because it's almost unavoidable brushing the tablet. Oh, I still didn't get it to work. Sorry about making the presentation rough, but it's doing things that I don't want it to do. Okay, one more time. 8.519. Because it comes out thicker when I write with a mouse. Okay, and then if you put that in a calculator, punch that in your calculator, 6.6864 divided by 8.519. Notice that, again, that's also, the bottom's only two figures, and the one on the top is two figures. So my answer is really going to have only two figures, and what I get is 0.78488 0.8554. And we only have two significant figures, but we're not going to count 1, 2, and then underline the 7. We're not going to count the leading 0 before the decimal, because leading zeros or zeros at the beginning of a number are not significant. So we're not going to go 1, 2, and underline the 7. We got to start on the 7 and go 1, 2, and underline the 8. And the following number is less than 5. So we will truncate all that. We will not round up. And our final answer, as good as we can get it, the best precision we can do, is 0.78. Okay, and that's going to be our final answer. So this is how you handle a mixed arithmetic problem. And it may well be, I haven't tried this one, so I don't know. Or if I did try it, it's been a long time ago and I've forgotten. But it may well be that if you round off every intermediate answer, if you had multiplied the 1.12 by 6.0 instead of 5.97, if you multiplied the 1.4 by 6.1 instead of 6.085, and if you divided 6.7 by 8.5, you might still have gotten 0.78. It doesn't always make a difference when you round off all the intermediate answers, but sometimes it does. And what I can tell you is when it does make a difference, the better answer is always the answer you get without rounding off the intermediate answers. Because again, every time you round the number, you change it a little bit. Over the course of a long calculation, all those little changes can add up. And that's the end of this PowerPoint. Now, originally I was going to follow this immediately with working the sample quizzes on significant figures in data and in calculations. But this was a rather long presentation. And so perhaps you need a break and I need a break. So in another session, I will record the working of the significant figure practice quizzes to help get you ready for the graded one. But as for this presentation, I'm going to go ahead and close it, and then let it send me the recording link so that I can get this posted for you, and you will have a tutorial on significant figures. So thanks for watching, and I'll probably post this before I post the other two, but I will be posting a tutorial showing the working of the quiz on significant figures in data, and then the working of the quiz on significant figures in calculations. So thanks for watching, and I hope you find it helpful.